Problem 3 on the test. How high a hill can a car coast up with the engine disengaged if work done by friction is negligible and its initial speed is 110 kilometers per hour? So looking at the conservation of energy in this problem, so we have this idea that the car starting toward the bottom of the hill, we've disengaged the engine, but it had an initial velocity of 110 kilometers per hour. So an initial velocity of 110 kilometers per hour converts to a velocity of 30.6 meters per second. All right, so our initial velocity is also 30.6 meters per second. So we're supposed to use energy considerations here. So that also takes out this angle piece because we'd have to incorporate the angle piece otherwise. So we're looking at the car having an initial kinetic energy here. And if we set the bottom of the hill, back of the car, as our 0 point, our car has no potential energy because he's at the 0 point. Doesn't have any gravitational potential energy. But we're going to disengage the engine is disengaged. So now the car is going to coast. So gravity is pulling it backwards. There's some component of the gravitational force of the weight. So it's only going to go so high. So what we want to know is how high can this go? When our car reaches this point, he's now going to have a gravitational potential energy. So we'll have a potential energy final. But I'm thinking here that it's going to come to a stop. At least that's what I'm reasoning that the question is saying. So it's not going to have a final kinetic energy. So that's going to go to 0. We have this equation by the law of conservation of energy. The total mechanical energy of the system will remain constant. Mechanical energy is kinetic energy plus potential energy. So I have my initial kinetic energy, which is 1/2 mv sub I squared. And I have my final gravitational potential energy, which is mass times gravity times height. Well, height's what I'm looking for. Right, we didn't need to know the mass of the car in this problem because it divides out. We're assuming no one flew out of the car, or jumped out of the car, or didn't lose a wheel or something. So 1/2 v sub I squared equals gravity times height. So 1/2 times 30.6 meters per second squared equals negative 9.81 meters per second squared times height. Now the tricky thing here is our change in kinetic energy is actually going to be negative because the car is slowing down. So our final kinetic energy would be less than our starting kinetic energy. So this is actually a negative value, which is going to take care of this negative value. So we're not really going to need to worry about that too much. So we're going to have 30.6 times 1/2, and then we're going to divide that by 9.81. So you're going to get a height equal to 46.8 meters. Part B then says that it actually is a 750 kilogram car that actually coasts to a height of 22 meters above its starting point. We still have the same idea. We still have kinetic energy initial plus potential energy initial equals potential energy final plus kinetic energy final. So in this case, we still have potential energy initial at 0, and we still have kinetic energy final at 0. So we still have the idea that kinetic energy initial equals potential energy final. Now, here's the thing though. This potential energy final is ideal when there was no work done by friction. So we have to account for some energy here that was done by friction, because that frictional force is slowing the car. So it's not going to allow us to get as high as what it would be without. So now we've got kinetic energy initial, which is 1/2 mv sub I squared, equals potential energy final, mass times gravity times height, plus this energy that we're looking for. So we have 1/2 times 750 kilograms multiplied by 30.6 meters per second squared equals 750 kilograms multiplied by 9.8 meters per second squared multiplied by 22 meters plus the energy that we're looking for. So I'm going to do the math here. So this comes out to be joules and this comes out to be so our final energy comes out to be, or rather, our energy lost due to friction comes out to be 189,270 joules. Now, part C says, what is the average force of friction if the hill has a slope 2.5 degrees above the horizontal? So now in part C, we're supposed to find in part C, we're supposed to find the force of friction. And we've got this hill now, and we've got an angle. It's not a very steep hill, 2.5 degrees. And we know that our car traveled to a height of 22 meters. All right, so we have to find the actual distance that the car traveled up the hill. So we need to find this distance to be able to find our frictional force. Remember, we're not talking about height anymore. Height is the difference from the 0 point to the top, not the length of the hypotenuse there. So in this case, we have to find the hypotenuse. Well, that's pretty easy to do. We're just going to say then that the distance equals the 22 meters divided by the sine of 2.5 degrees. So the total distance that the car travels up the hill is 504 meters. We know that the energy loss due to friction is 189,270 joules, which is also equal to the work done by the force of friction. So the work done by the force of friction equals the force of friction multiplied by the distance. So the 189,270 joules equals the force of friction, which is what we're looking for, multiplied by the 504 meters. So if we do that calculation, we get the force of friction equal to 376 newtons. Oh, sorry guys, went down beneath there.